Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. I invite you to watch the video. Applied Operations Research and Industrial Engineering and learn more about AWO. A company's value chain is made up of two chains, strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. The diagram presents the chain of the company's production chains that together make up the value chain. One of the greatest evolutions in the modeling of companies occurs in the interpretation of their value chain. The diagram presents the evolution of different administrative practices in companies, which are linked to technological solutions, leading to AWO. Thanks to computational power, the integration process has continued to grow. The diagram presents the original S and OP model, and the current version, which integrates more and more models. This evolution has led to modeling based on artificial hypothalamus, supported by the integration of mathematical programming and artificial intelligence. The power of today's technology is not in the mathematical calculations it allows to be performed, it is in the mathematical calculations we can imagine we can perform. Structure. The group of courses aims to train the participant in the main problems that need to be solved in the planning and advanced programming of value chains specific to industrial engineering, and more generally to engineering. It is made up of 4 courses in applied operations research. Industrial supply chains. Agro-industrial supply chains. Demand chains, and transport and logistics chains. Courses can be taken all in a group or individually, depending on the student's interest. Transport and logistics operations chain optimization. Training in the problem of optimization of the logistics and transport chain, concentrating on the modeling of modern multimodal transport systems, trains, ships, planes. The following types of optimization models are studied. Optimization of routing problems, such as TSP, travel salesman problem, and VRP, vehicle routing problem, and their continuous time modeling. To produce detailed schedules. Optimization of brokerage prices in LTL, less than truck, type transport systems. Optimization of special transport systems, ships, planes, trains and truck fleets. Optimization of logistics operations in the environment of ports, airports and railways. Optimization of multimodal transport systems, and optimization of the processes of buying and selling products in international markets. Aimed at professionals, engineers, mathematicians, physicists, consultants, economists, data scientists, software developers, etc., who require and or wish to know mathematical modeling, advanced analytics algorithms, related, among others, to the implications of Industry 4.0 and its relationship with the process of evaluating the technical economic impact of the decisions that are made. This continuing education program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and or supervise, with propriety, the professional functions in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of the companies. Mathematical methodologies. Mathematical methodologies correspond to the scientific foundations for implementing mathematical optimization models. Specific objectives. Training in fundamental methodologies to support modern mathematical modeling. To train so that the mathematical modeling of industrial and business processes is a generator of real socioeconomic wealth frequently used in our society. Understand that optimizing the use of resources is the scientific basis of sustainable development. Learn about systems and industrial market modeling. Learn the fundamentals of modeling real problems based on the integration between mathematical models and data models. Information technologies. Computer technologies correspond to the computer tools available, freely or commercially, to design and implement solutions to problems in social or industrial organizations. Specific objectives. Learn how to implement solutions applied in the real world by making use of the modern computer technologies available for the algebraic modeling of industrial and business systems. Present and manage live tools used by large companies to solve their optimization problems. Understand the state-of-the-art of optimization and its relationship to smart computing. Know the available technologies, as the principle of basic knowledge to be able to solve, in reasonable times, problems with millions of variables. Know the fundamentals that must be had for the assembly of models using the most effective technologies. Value chain optimization or enterprise-wide optimization.
El diagrama presenta la cadena de las cadenas productivas de la empresa que juntas conforman la cadena de valor. Una de las mayores evoluciones en el modelado de las empresas se da en la interpretación de su cadena de valor. El diagrama presenta la evolución de diferentes prácticas administrativas en las empresas, que están vinculadas a las soluciones tecnológicas, que conducen a EWO. Gracias a la potencia computacional, el proceso de integración ha seguido creciendo. El diagrama presenta el modelo original SIOP y la versión actual, que integra cada vez más modelos. Esta evolución ha llevado a la modelización basada en hipotálamos artificiales, soportada en la integración de la programación matemática y la inteligencia artificial. El poder de la tecnología actual no está en los cálculos matemáticos que permite realizar, está en los cálculos matemáticos que podemos imaginar que podemos realizar.
Optimization of transport and logistics chains. General plan of topics. Key topics: fundamentals of optimization and economics, augmented artificial intelligence, artificial hypothalamus, enterprise-wide optimization technologies for mathematical optimization. Use cases: modeling of routing systems and scheduling of activities, continuous time modeling. Travel seller problem, TSP, vehicle routing problem, VRP, container packing problem, BPP, optimizing large-scale logistics operations port, ship and maintenance coordination port logistics operations designing resilient distribution systems optimization of distribution and production center layouts inventory policy optimization optimizing global sourcing ATP, available able to promise, systems. Revenue management in LTL transportation systems routing systems 4.0, real-time distributed routing optimization routing using intelligent traffic systems, example WAZE, vehicle speed optimization and energy efficiency. Complex product distribution and or picking processes. To be effective, planning the distribution and harvesting of complex products requires mathematical optimization models. For example, in the case of propane gas, LPG, the objective is to support the weekly and daily scheduling and operational rescheduling of truck dispatch. The modeling hypotheses are as follows. Vehicle fleet composed of multiple types of trucks and multiple types of LPG trailers. Trucks can be moved with or without trailers. A truck can tow certain types of LPG trailers. LPG trailers can be dispatched with or without cargo. Vehicles move between nodes, or terminals. In the nodes there may be demands that must be satisfied or purchases that enter LPG into the system. In the nodes there may be demands that must be satisfied or purchases that enter LPG into the system, and there may be LPG storage tanks in the nodes. The modeling of this type of transport, in bulk, will be analyzed in detail. Real-time transport routing distributed optimization. New technologies and the large amount of permanently generated data, big data, changed traditional moment-based optimization to real-time event-based optimization. Models will run autonomously, when necessary, by events. This implies that each component of the system, agent, needs to know what information it needs to take from the intelligent metering systems and what information it must provide for other agents in the system to make their decisions, using asynchronous parallel optimization methodologies, to keep the system, from end to end, on the path of optimality. In the case of freight transport, the process of planning logistics operations in a city, or in a metropolitan region, could be carried out as follows. At a given time of day, the central dispatcher comprehensively plans all routes, sequence of customers per vehicle, to fulfill the day's delivery and/or pickups. This involves solving the VRPTWTDTT, vehicle routing problem with time windows and time-dependent travel time, problem using an optimization model according to the company's business rules. Each route must be loaded into the vehicle on a mobile smart device, VDO, iPhone, iPad, through which measurements and information are received from a smart metering system, like WAZE, which provides the road, street sequence, and the best estimated travel time. During the route, at the end of the service in a customer, the VDO requests information from smart metering about the estimated travel times in real time. With the new information, the VDO can solve a TSP, travel salesman problem to recalculate the optimal route to follow to serve the missing customers and send that information to the central dispatcher, who, if necessary, will reorganize the planning of all routes. Real-time energy consumption optimization. Fuel consumption can account for up to 63.9% of the variable operating costs of a heavy land transport fleet, therefore, it is a critical factor in truck route planning and scheduling. In the latest generation cargo transport vehicles, the engines are electronic, digitally controlled, with telemetry capability from the nearby environment that allows fuel efficiency to be optimized. This autonomous capability of modern vehicles can be called optimal short-range control. There is another level of operations planning for a fleet of vehicles that is long-range and must consider the vehicle's route and planned arrival times. The importance of this planning is seen in the performance curve of an engine in which operating in a range of 1,100 to 1,500 rpm obtains optimal fuel consumption and operating between 1,500 and 1,800 rpm obtains optimal power performance with higher fuel consumption. Optimizing energy consumption is complex because the consumption function is nonlinear and depends on factors that are the result of decision-making such as the load and the geoposition of the vehicle. Route-dependent factors can be divided into static, e.g., slope, roughness, and dynamic, traffic, weather condition of the route. Although the mathematical problem is complex, the power of parallel computing, the effectiveness of optimization algorithms and online databases allow it to be solved in the environment of Industry 4.0. Less than truckload revenue management optimization. The central problem of an LTL, less than truckload trucking, corridor is choosing the demands of the most cost-effective transportation services, for direct long-distance routes or for multiple pickup and delivery routes, and setting the bid price for requests for transportation services or acceptance of an offer previously agreed upon in a long-term agreement. An LTL network consists of a transportation company with a fleet of trucks, which serves a sequence of delivery requests, received by phone, mail, or the internet. The solution is to implement a DSS for LTL revenue management that must have the following models. Winning price bids to serve freight forwarders, determined by machine learning, ML, models to segment the gap between winning bids and losing bids. Winning price bids prices to be paid to carriers, determined by ML models to segment the space between winning bids and losing bids. Link the flow through the LTL network with the ML models for revenue management that define winning boundaries for price offers. The diagram presents the flow of data between the mathematical models and information systems associated with the partial load problem, LTL. The course director is the founder and scientific director of RCADT. Engineer Velasquez Bermudez's experience in applied operations research dates back to 1972, which means that he has accumulated more than 50 years solving real-world problems, doing engineering consulting using mathematical models. This is the technology transfer that those attending the course will receive. The table presents the plan of topics planned for the module optimization of transport and logistics chains. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.